So for the next technical session, which will be on robotic restoration via laser additive manufacturing, please put your hands together as we welcome Mr. Ramesh Singh, PhD, GK, Devarajulu Chair, Professor and Associate Dean, Infrastructure Planning and Support Department of Mechanical Engineering, IIT Bombay. Huge round of applause. So I hope you all are still filling out the forms and our team will be collecting them soon.
Good afternoon. Thank you for inviting me for this. So I don't like podiums. I'm an academician, so I'll walk and talk. So what I'll talk about today would be development of autonomous robotic restoration process. It's tongue twister, but apparently what this is, it's basically a very sophisticated way of repairing dies, what you do in industry at regular basis using your welding electrodes and stuff. So we'll do a more scientific way of kind of repairing the molds. So I'll basically talk a little bit about IIT Bombay because that's where I come from, and a little bit about the institution, my department, and also my lab. I do engage with industry quite extensively, so this will be a good time to kind of showcase what our strengths are and what do we work and what areas do we work in. So that would be one thing. And then finally I'll talk about, finally I'll talk about basically development of a robotic restoration system, which actually was a industry, academia, and the government partnership. So there were a lot of players in this, and finally we worked together, and still work in progress, but a lot of it has been accomplished. So I come from IIT Bombay. This is IIT Bombay, this is Bombay, so a lot of people know about us. But for those who don't know, we are in Bombay, and we are blessed with a very good campus. We share a boundary with Sanjay Gandhi National Park, so we do have some visitors, very curious creatures. Sometimes we have crocodiles in the lake, and also sometimes leopards. So in fact, one day there was a leopard sitting in the lab next to me. So my folks get out and there was a leopard right there. So other than students, we do have some other learners too. So that was on the lighter note. We have 16 departments, about 750 full-time faculty, about $40 million of research funding. This keeps on fluctuating between $40 to $50 million. I use these numbers because I also give these talks. So it's around about 360 crores, the last year's research funding budget for us. We have about 14,000 students, and the general notion is that IIT is an UG institute, which it is not. About 55 to 60% of the students are postgraduates, about 4,000 or 30% of the students are PhDs. So we are a very, I would say, postgrad-centric institution and not primarily UG institution, which people generally think us to be. Of course, we are the highest ranked university in the country globally. Our mechanical engineering programs is ranked about 57 in the world. So we are significantly well-ranked, well-positioned in the global framework of rankings. Coming to my department, we have 62 faculty, about 300 PhD students, about 250 MTech students, and we have decent amount of funding and publication, which is the metric for our basic productivity. But one thing I would like to talk about, we also have a program which we started for Bharat Forge actually. So this was MTech in materials, manufacturing, and modeling. And what we did was we had people who were working on the shop floor. So these people had 12 years of experience, 8 years of experience, who were experienced people. And the idea was, since they have the knowledge of industry, what we do is we train them in materials, new materials, how basically analyze the materials, manufacturing techniques, and also some mathematics, basically to be able to do experimental design, some statistics, and things like that. So these people will be very valuable because now they have been equipped with, they have the basic knowledge, but now they can do higher order work. And this we did for Bharat Forge, and we trained about, if I'm not wrong, we did it for 5 years, and close to about 75 or 80 engineers we trained. And these guys, now they actually man their KCTI, Kalyani Center for Technology and Innovation. So, and these guys are really good because they have know-how of manufacturing. And whatever they do, this skill upgradation we call it, right, goes back to the, sorry, it's I think timed for some reason. Yeah, so this is one of the programs which we did with the industry, and it's very successful. So now I'll talk about a little bit about my lab, where I come from. So my basic, I have 4 research verticals. The first one is micro machining. So all of us do machining, right? So we see tools which are of the order of few millimeters. But what we do, I use tools which are fraction of human hair, 1/4 of human hair, and we machine things using that. We create components which actually go sometimes in terahertz components in space. A lot of times they are micro molds and things like that. So this is what we do. We actually develop the machine also and the process also. Those things we do. And then the second research vertical is something called flexible reconfigurable fiber laser manufacturing. There what we do is we have a laser source with multiple fibers and we change the heads and we can do different process. I can do additive manufacturing, I can do cutting, I can do texturing, I can do hardening. With same laser, same fiber laser, I can do multi-processing. And we create stations for that. One of the examples I show you through my talk. And the third vertical is basically, again, analysis, which as an academician, that's my primary mandate to do. But the last vertical is very industry-centric. We know that there's a technology deficit between Indian industry and the Western counterparts. And this is something that needs to bridge. And what we feel is that, for some reason, we have not been able to develop this last-mile translational ecosystem. We do a lot of good work in labs, but somehow it doesn't really see the light of the day. So this is something I work on very closely. So we work on typical industrial problems. So we have made machines for CEAT, which have been deployed in actually their Halol plant. And also we are developing systems which will be deployed. So these are special purpose machines. We do both ways. Some things we work in the lab, and a lot of times we take the unmet needs of industry, work on them, develop a product in the process, and basically give it back to them. And these are some snapshots of the lab. We have 5-axis machine, we have hard turning center, we have laser cutting machines, deep hole laser drilling machines, micro machining centers, electrical discharge machining centers. And we have one of the best characterization facilities in the country. We have a CMM that was donated by Mitutoyo. Mitutoyo gave us free. And then we have systems which are automated, basically optical CMMs, surface measurement devices, and we have best form and surface measurement facility in the country. And this is just to kind of showcase how we get our funding from. So we get about a lot of funding from the government, and we also get specialized funding for developing these lab facilities. So there are 2 ways of funding, one for development of a scientific project we write, and then we get earmarked grants for basically facilities. And also what I do is in my case, about 50% of my lab funding comes from industry. So we work with various companies. We have worked with L&T, we have worked with Bharat Forge very closely, Aditya Birla Science and Technology, a lot of MSMEs. Jack Chemicals is a company where I'm working with, Technocraft. So a lot of these companies we work with, and basically we give them solutions. So a lot of the work we do is just not intellectual stimulation, but also hardcore technology development. So this is a long list. I'm not going to go talk about it, but then there were some issues. People were talking about polishing, right? Polishers are going away. So there are technology solutions for that. So for the first thing what I did was we developed actually a conformal hydraulic polishing process that was basically for BARC for a very strategic application. But what we did was we made a machine to polish sapphire. So basically we make a machine, and this can actually be done on a CNC, so you can do freeform polishing also. And there are technologies called elastic emission machining, hydraulic nanopolishing, which can actually reduce your dependence on human polishers. So there are technology solutions for things which you feel that the human beings you're not able to find to do that. The other thing what we did was, right now I'm working very closely with Bharat Forge, basically trying to look at their coating degradation or enhancement of coating, and also doing something like mold hard facing and repair. And then we are doing something for the spinneret development. These spinnerets are whole bunch of holes, which are 200 micron holes, 300 mm deep, not 300 mm deep, 3 mm deep. So that's the depth of the whole aspect ratio. So we are basically creating machines, and also developing the machines and the process for doing this. And in one spinneret, so this is just if you see in the bottom right, so you see these are 20 holes. But actual spinneret in industry would have 55,000 such holes. So you need to be able to create machines to create such precise holes in large numbers at a affordable price. And these are some of the machines which we have developed. So we actually developed one machine for tire metrology. The problem was that when Seat was building tires, their edges were not aligning. And they were not able to measure it accurately what was happening. So what we did was we developed a system with 2 cameras and basically did image processing and gave them on their, whatever the quality software was there for their QA QC team. So it will say that whether it meets the quality requirement or not. So that complete system integration building, we did it for them. And then the other thing which we did was something called this laser vent cleaning. So all of us know that these tires have these vent spews, right? The hair-like structures, new tires you see. Those come from the vent. So when you mold the tire, when you do the curing operation, after a certain number of cycles, the vent gets clogged. So what they do usually is they use this small drill, about 6 micron drill, to basically clean the holes. Now the problem with this drill is that drill can break. Now it can either clog the hole, or what it will do is it will go in your rubber of the tire. And both are very dangerous, right? If there is a imperfection or basically a defect in the tire can explode. These days, these are tubeless tires, right? So now, they said that we don't want any of these mechanical drilling, manual drilling. So what we did was we built a system. There was a vision system which will find out where the hole is, fire a nanosecond pulse laser multiple times, and then blow away all the debris. Completely automated. We said that we'll completely automate the process. You don't have to worry about it. The machine will not take any restroom breaks or anything. So you can have a very precise process. And we actually installed it. I went personally and installed this machine there. And then we also build this machine, this micro machining center, which we talk about, right? This we have started a company. My PhD students have a company which actually markets the machine, the process, and we also provide both fabrication services and the machines to various people. We actually export some of the things as well. My students' company. Now, all this was just the introduction of what we do. Finally, what I'm talking about is a single project which was industry, academia, government collaborative development of this robotic restoration system which I talk about. So basically, I'm preaching the choir here. Everybody knows what. So this aerospace components, dies, molds, boiler tubes, they are all subjected to thermomechanical loading, right? And these are very high value items. I don't need to tell you that. You guys know much more than I do. And existing damage repair, right? When your mold is expensive, it gets damaged. What do? You gouge out the material and fill it with a welding electrode, polish it, and say it's good as new. But the problem is it's a very ad hoc way and very imprecise way of repairing it because of the main things, right? Because you don't know what kind of residual stresses are coming, right? So if the residual stresses are tensile, it will not last even 4 or 5 cycles. So if you understand it scientifically, so the key challenge is if I were to do completely automated restoration. So say if a defective die comes to me and I want to repair it, what would I do? I would need to create a system where it can scan the defect, it can deposit the material, it can finish it, it can inspect it. Complete autonomous, no human intervention there. So if I were to do that, there will be 2 challenges. The first challenge will be creation of such a system, right? So such system would need some sort of a manipulation device, a deposition device, a scanning device to basically find the defects, and finally, inspection device. So one component will be just developing the physical system. The other component is how do we understand the process? Because if you don't understand the process fully, in that case, whatever I do would be not sustainable. It will fail very easily. So one of the things I want to understand is when I'm depositing, especially steels, right? I'm depositing steel on a mold. What will happen is there will be differential thermal contractions. There will be residual stresses because you're depositing hot molten material on top of a cold bulk of the steel. So there will be differential thermal contraction and that will create stresses. Not only that, because the rate of cooling is very high, there will be metallurgical transformations. And combined effect would basically decide what will be the life of your die. So you need to understand the science. So one of the important things which I talk about always is whatever technology you develop, if it's not science enabled, it will not be sustainable. So that's what I talk in all the forums, every place, that technology has to be science enabled. So these are the work packages. What we did was we first wanted to basically develop all the scientific understanding, which may not mean much to you, but I'll basically give you some of the gist why this is important. Then we made a lab scale setup. Based on that, we went to the government and said to give us money because we can show you a proof of concept, but then real system actually requires a lot of money. So then development of a complete system. and then testing and characterization, and finally commercialization and product marketing. So we had players for all these. Some of them are SMEs, some of them are big players, but the idea was everybody will come together and develop a product. So don't get lost in the equations. Don't worry too much about it. But what we did was we created a model for basically this additive manufacturing thing. So there the material gets deposited, it basically gets cooled, it solidifies, and it undergoes transformation and differential contraction. So basically what we do is we are able to capture the strains due to volume dilation, because what happens is when phase transformation takes place, if you cool it very fast, it will go from one which is called BCC to BCT, and there will be physical growth in the volume, and this will create strains. And if you don't account for that, what will happen is we're not able to know what kind of residual stress will be there. And if your residual stress is tensile, in that case, if there is a small crack, it will propagate. So if you understand that fully, you will have a much better quality of deposition. So that's the moral of the story here. So what we did was we developed this model, we did the testing. So we went to a neutron diffraction, which is a really fancy thing, measured the residual stresses, bulk residual stresses, and then finally calibrated the model. Then with all this, our goal was to basically define something called, which is called critical linear mass density. So what we can do is, we can deposit certain material. It so happens that the maximum tensile stress lies at the melt interface. So what you can do is, you can push the melt interface low, and because of force balance, the top layer will be compressive. So if your deposition is compressive, meaning that you don't have to do a secondary treatment. You don't have to do heat treatment, you don't have to do shock peening to have compressive stresses. So your material as deposited can have very high compressive stresses. So this is what we got from this model. We said that just by virtue of deposition, you'll have compressive stresses, so you don't have to do secondary treatment, no heat treatment, no shock peening required. Then we did an even more sophisticated model, which actually captures the laser particle interaction, the particle falling in the melt pool evolution, and finally the deposition geometry evolution. I'm not going to the details, but finally the idea was I have a very sophisticated model, but what do I get out of it? What do I get out of it? There are three basic requirements when I'm doing additive manufacturing. The first one is, if I'm depositing, if my deposit is very, very high, in that case, my deposition angle will be obtuse. And what will happen is, between two layers, I will have a gap. So this will create porosity. So I want to know that always my deposition should be acute. The other thing which I know should be that my depositions should also have adequate bonding. So my bonding between substrate and the deposit should be complete. So all these three maps, the first map shows, and the third map, the entire deposition should be under compression. If there are tensile stresses, means the crack can grow and I will not have good life. So all these all these simulations, what we did was, we got process parameters where I will have good clad. So in the top, if I go in this laser power scan speed combination, this process combination, I get favorable deposits. If I go D by D mean greater than 1, if you see that green and below, those are favorable deposits. And finally, again, if green, if you see blue and green, these are, so blue, green, this side, compressive stresses. If I go from sigma into 0 to this, so this combination would give me favorable compressive stresses. So all these simulations are giving me process parameters to work with. So this is not just intellectual stimulation, these are functional process parameters which I can use on a real machine. Then, so all the science done, just to give you some brief overview, the science has been done. Now what we did was, first thing we did, we developed a lab scale setup. In the lab scale setup, we made a nozzle, we made a kind of a stopgap powder delivery system, and built in some small features. So this is something we 3D printed a nozzle and basically devised the complete system with a 100-watt laser just to do the proof of concept. Then once we had the proof of concept, we went ahead and actually started building a large-scale 5-axis or 6-axis robotic or 5-axis DD system for restoration. And then we did some characterization of the process once we built it. Then what we wanted to do is, we wanted to do it completely autonomous, right? Otherwise, we are all talking about skill development, skill development. So one way to address skill would be enhance the technology. So you have enhanced technology where you can do automated scanning, you can do automatic deposition, you can do automatic inspection, and finally out comes your product. So what I tried to do was very audacious. I said that I have a defective mold, I'll go ahead, scan it, I'll deposit the material, I'll finish the material, and finally inspect the material. So there will be no human intervention. That's my dream. We are far from there yet, but we have done 2 modules. We have done freeform deposition, we have done damage detection. And the other 2, finishing and inspection, is in the pipeline. And then I'll give you some of the examples from industry, what we did. So this system has, so this deposition system has a manipulator, robotic manipulator, a deposition head, a laser, a 3 kilowatt laser, and also a powder feeder to feed the powder particles. So you can either have a powder feeding system or a wire feeding system, both you can do, and both we have in the lab. Wire feeding is a new thing which we are still developing, but powder feeder is fairly matured. We have done a lot of work with the powder feeding systems. And then I'll just show you a small video how it works. This is a system. This is a first generation system, so mind, this is the very first generation system. Second generation system is much more sophisticated. This is something we're doing, this hard facing for, on H13 we are doing some CPM 9V, some crucible steel, very hard crucible steels for Bharat Forge. So that was the first generation. Now we have made it look more professional. There are 2 things. One side there is a robotic system with about 1.2 meter complete length. So I can do about, with some gap I can do a lot, easily 1.2 meter I can handle. And if on the back also I can handle because it has like a complete 360-degree thing. I also have a 5-axis system of doing 1 by 1 meter, both built on a single platform. So if you see on the left, this is how the machine looks, very compact, completely developed by us. All the system integration was done by us. By us, I mean my students. I can't take the credit, but they have done it. Some of the things which we have done is, you imagine this is what we have built. This material is crucible steel. The yield strength is 1.6 GPa. If you were to machine something like this, it's a nightmare. But you can deposit it. So other than just repair, you also have this luxury of depositing super hard materials on top of your existing thing. So what we can do is we can actually not only repair your mold, we can make it better than what it was initially. That's what we propose. So that was the deposition system. Now what the problem is that I also need to be able to know where the defect is. So if my mold is damaged, I should be able to do the damage detection. So what we do is we use a laser scanner and basically get the data from the laser scanner and the robotic encoder and fuse the information and create 3D point cloud. So get the data, and from data we also develop algorithms to do the edge identification, and then basically what kind of geometry is it we can identify. What we have been able to do is we have able to identify about 80 microns of defect. So that is our resolution. So with this system we can 80 micron defect size, diameter defect size I can easily detect, which should be more than required for any functional damage on the mold. So I'll just show you a small video of the damage scanning system. This is just a simple thing, but we can do a lot more complex thing, just to give you kind of a. So it basically gets the data and then give you a 3D map. It can also detect free-form shapes. So if you have not only flat, if you have a shape with form, that also it can detect defect on a form object. So what I will do is, then we did some work with Bharat Forge. So there was their punch, which we wanted to do hardening. This is my last slide, so I'll just. So this is basically what you do, a turning process. I'm depositing there, and I also do the face deposition. This is a real punch from their shop. So I'll just stop here. So we can do either using a robot or a secondary axis. So this is my last slide. I'll just summarize. So the idea is that we create systems to do autonomous repair, and this can also be used for other things, for 3D printing, for surface modification. And the idea would be that we create, we want to transfer technology to MSMEs. We also want to export this and basically create a startup ecosystem. And basically, the idea would be work with industry to mature these technologies. A lot of it is still very fresh. So it needs some time and some adoption to be able to mature these technologies. So with this, I'd like to thank my students. They have done all the work, I take the credit. So thank you. Sure, sure.
Thank you once again, Mr. Ramesh Singh. And I think we are all students of life to begin with, and we are always learning from different domains. And of course, this is a celebration of the tooling industry. Huge round of applause for him, and to felicitate him formally, may I request Mr. Raj to join us here on stage once again. Mr. Raj Singh, please, the EC member, put your hands together for these gentlemen right here. Calls for a perfect photo op.
Thank you so much.
Thank you, gentlemen. You would want to collect this? Yes. We'll get the stage set for the fireside chat. We'll need 2 chairs on stage.